of script x, okay, is defined to be limit n goes to infinity, 1 over n joint entropy. Okay, joint entropy divided by the length of the sequence. So this we will call per symbol entropy. Okay, and it says when it exists, right? Because we are taking the limit, right? We have to worry about if the limit exists or not, right? All right. When x1, x2 are IID, the rate attains the maximum, which is hx1. Okay, it's obvious, right? Because if these are IID, basically joint entropy becomes sum of entropies, right? Like this one. And then since we have n at the numerator and the denominator, so we can cancel them out, so we can have hx1. When they are independent but different distribution, then basically the joint entropy is just the sum of entropies. Okay, that's it. And then we define something called conditional entropy. So let's say h prime, okay, instead of h in previous page. And this one is, conditional entropy, like this, okay? Right, and we let n goes to infinity, okay? And for a stationary process, basically, per symbol entropy is equal to conditional entropy. Both limits exist and equal. That's what this statement is about, and probably we will have to prove this, right? We will prove this with Cesaro mean. Basically, we can evaluate this, right? First, and here I say this one is smaller than or equal to this one. Can you say why? So here, only difference between left and right is the disappearance of x1 from the left. So, and then I say the inequality goes this way. And then I want to ask why to you. Conditioning reduces entropy, right? So this one is smaller than or equal to that one, because x1 is included here, and then x1 is not included here. So this one is, in general, greater than or equal to the other side, which is this one. And then now I say that this one is equal to that. What's the difference? I have translated this relation one step downward, right? From n plus 1 to n to n minus 1, and so on, right? And then why? Because this is, I said, stationary process. Aha, then this one, comparing these two things together, these two, that one is larger than or equal to this one. So, then this sequence right here that we want to investigate is a non-increasing sequence of numbers, right? Non-increasing sequence of numbers, okay? It is decreasing or stay. That's what it is, right? So non-increasing series of non-negative numbers, okay? And it is bounded from below. What is that below? The trivial one. Greater than or equal to 0, right? So it is non-increasing, so sometimes stay, sometimes smaller. So in the long run, 0 approaches 0, right? Or may not approach 0, may just stay at a certain number, right? And then the limit exists. So convergence from above, right? Because it is bounded below, it is either converges to 0 or some number between this number and the upper bound. Okay? So the limit exists. So having said this, we can say that we can use the Cesaro mean from analysis. Basically, there is a sequence converges to a limit exists. That's what it means. So this one is the conditional entropy that we were talking about in previous page. And then it converges to a number, right? And then Bn is a 1 over n times sum of entropies. That is basically this one is, right? So Bn, Bi are non-negative numbers, right? And then we want to show that if this is true, if this is P, then Q, right? Q is Bn converges to A, okay? So if An converges to A, Bn converges to A as well. That's what it is, okay? And then we can show it. But that one is very easy, right? Just by understanding this picture, we can understand the proof, okay? So if we consider Bn minus A, basically that is 1 over n. By the definition of An, we can apply it, then we can show that that is this summation of that number, but this summation of number where the number is finite, basically sum of a finite number all the way up to n epsilon, when n is epsilon is defined to be this number n here, before convergence here, after ne, things have converged. So these difference Bn minus A is within the boundary of epsilon, plus epsilon and minus epsilon. Okay, all right. Then basically we can break this into two summation. One summation is I running from 1 to n epsilon plus n epsilon to infinity. But each number is smaller than epsilon for the infinity summation part. So basically we can have epsilon outside, and then basically we can have that one to be epsilon. And then because this number here is a finite number, then divide as n goes to infinity, this one goes to 0. Okay, so basically that's a Cesaro mean, and that's basically it. And this is another more rigorous proof. You can take a look. But if you have understood this using the picture, then you don't have to see this. Okay. So basically, we can say that the possible entropy and the conditional entropy is the same for a stationary process. So using the chain rule, we can say this, and then applying the Cesaro mean, we get the entropy, possible entropy is equal to conditional entropy. All right, then what is the implication? So the understanding implication is more important than this mathematics. So for a stationary process, we can compress. How do you calculate the amount of compression that you can do? Just like in the IID case, we can use this entropy rate, right? And multiply by n, right? And then there are 2 to the power of nh typical sequences of length n. Same story, right? For non-IID case, right? And then the probability of a typical set is close to 1, right? As n goes to infinity. And then nh bits are good enough to represent the sequence, okay? So that's it, right? So what is the possible entropy? H. What is the entropy of a sequence of length n? nh. That's it. Okay? So that's the basically is the story. And then if you do this for a Markov chain of order 1, then basically you can show this, okay? Because that one is equal to that Okay, and then for a stationary distribution Markov chain, you can find P, then you can obtain S, and then you can also find out the HX given this way. All right, that's basically it. And then entropy of a two-state Markov chain is given right here, like we have done in chapter 2. All right, so that's basically entropy of sequence of variables stationary Markov chain case. Okay, and now let me show you this example. See section 7 of his paper, Shannon's example of a Markov chain. Basically, he was interested in finding the entropy rate of an information source, English, right? And how much redundancy is there in the source? Redundancy in English is like 50%. That's what the empirical finding tells us. And then I would like to give you an example here, this one. Why do you think we can compress English source? Can be gleaned from this very simple example. Okay, take a look at this. Okay, so is there anyone who can decipher this message right here? So if someone has a Markov chain table like that, the person can exactly decipher with the high probability selections, right? This one. So, but since we are human, we can be better at that, right? So can you take a look at what it is? Can you decipher? So here, where underscore is the place of letter missing, okay? 잘 안 보이나? So, so here we have 13 letters deleted out of 40. So if you are able to, or that model, that the Markov chain model can decipher this, right, with a probability of let's say 99%, right, then we can show that, English sentence can be compressed. That's the idea, okay? How much? Like 33% in this particular example, okay? So can you decipher this? Anyone? 이거 내가 미국에서 강의할 때는 미국 학생들이 바로 얘기하더라고. 이거 한국말로 했으면 금방 알아듣을 텐데. 요거 뭐가 빠졌을 것 같아요, 여기에? 내가 하는 말이야. 내가 노는 걸 좋아하는 사람이잖아. I want to. I-W-A-N-T. Want to go home and play with my kids. 그렇잖아. 그러면 이게 컴프레션이라니까. 그러면 so we have deleted 13 characters or letters here. So 13 out of 40, 33% was removed. But we will still be able to reconstruct the whole message. So compression algorithm can be like that one, Markov chain, designed, and then we can design a decoder as well, right? How do you do the decoding? Run that algorithm, right? Because we have a probability distribution. Right? For each previous letter or two letters, we can find the most probable next letter, right? You can do that, right? And then that's the compression, okay? So 그 다음 페이지. So 맞았어요. I want to go home and play with my kids. All right. So that's the. So now we are ready to go to data compression, which is chapter 5. But I will do this next week. Okay. All right. And then before you guys go, we need to determine the midterm exam time. Like I learned more from the 두영수 학생 that they are using the college, the GIST college is using some systematic rule, right? If Monday and Wednesday, right, first and third, and then second and fourth lectures are given, then we have to follow a certain rule to do the exam in a midterm week, right? And then probably for the final week as well. So bottom line is that Youngso has to take the exam, can take the exam from 1 to 4 on Monday in the midterm week, right? But we are graduate school students, right? We usually do in-class midterm, right? So what I can do is we can utilize Monday 1 to 2:30, which is usual class meeting time, so that he doesn't have a conflict. None of you have a conflict. Works for everyone, right? 그래서 여기다 쓰면은 타임 컨플릭트 없는 타임 시간은 Monday, 이게 며칠일 날이지? (24죠) Monday 24 1 to so 13 to 14:30 이렇게 하면 되죠? 네. 수요일은 쉬어야지. midterm 봤는데. midterm 위기잖아. 이 학생은 시험 보러 또 가야 된다니까. 그러니까는 못 하는 거잖아.
시험 스코프는 어디까지?
시험 스코프. 그거는 midterm 전까지 렉처 노트, 그 다음에 텍스트북, 그지? 그 다음에 비디오. 비디오에 뭐 내가 문제 풀이도 해줬잖아. 비디오에 보면. 그죠?
다음 주 수업 시간 한번까지 다 포함된 건가요?
다음 주 다 포함은 아닌 것 같고 홈워크 내준 데까지는. 챕터 4, 5까지는 빨리 끝내놔야 그 재밌는 거를 midterm 끝난 다음부터 할 수가 있어요. 왜냐면 챕터 5가 boring이야. 되게 boring이야. 컴프레션은 boring하다고. 그러니까 lossy compression 파트로 가야 이제 수학이 많이 나오고 재밌는데 챕터 5는 그냥 컴프레션이거든. lossless compression. 그래서 너무 쉬워. 그래서 그냥 읽으면 다 아는 거니까 그거 빨리 겪고 지나가자고. 제일 힘든 게 챕터 2. 챕터 2를 이해하는 게 제일 어렵고 그거 이해하면 나머지는 뭐 쉽잖아.
그럼 다음 주 과제가 4장과 5장까지 다 포함되는 거예요?
Yeah, so I have to say it in English because there are non-Korean speaking students here as well. So the question is 뭐지? 까먹었어. What was your question? So what is the coverage for the midterm, right?
Yeah, and the scope of the next homework.
Homework 1, 2, 3, 4 inequality. It's intuitive one I would like to do here. Let's say here. Markov chain inequality. Markov inequality, sorry. Here I have a random variable, right? And then here omega 1, omega 2, omega 3, omega 4, for example, like that, right? And then on this one, I have a mapping to a real number or a non-negative number in this case. I would like to do. And here is the 0, and here is a number, right? Right? And then this is the mapping. See? For example, like that, right? Mapping. So it's good. And then each one with the probability distribution, right? So probability is given. And then we can consider, let's say, number t, right? Number t. Aha. These outcomes has we can say it x omega 1. This one we can call it x omega 2, x omega 3, x omega 4, like that, right? And then, as you can see, x omega 2 is smaller than t in this particular picture, right? Rest of them, x omega is greater than t. All right? Then I can talk about a set of omega where x omega is greater than or equal to t or small. So we can talk about two different sets, right? And then I can say this. Let's say indicator function of omega and let's say AT, set AT. So I can define let AT to be collection of all omega where x omega, I can define this way, right? It's a legitimate definition of a set, okay? And then I can define this indicator function to be 1 if omega belongs to that set, or 0 otherwise, okay? And then I want to compare this with x omega. So for each omega, I can do the comparison, right? For each omega, I can do the comparison. But since I have a t here, but this one is 1 or 0, so I'll multiply this by t. Multiply this by t. So this whole thing is a random variable defined to be what? If omega belongs to this set, t, otherwise 0. That's what this random variable whole thing is. Here right now is I have defined only for this part. Only this part. T is a number. Okay? So what can you say about the inequality? Which one? 1 or 2? If you can answer this, that's the Markov inequality. Can you answer this? 2. One person says. 아, 이름 또 까먹었어. 미안해. 성규가 대장이에요. 성규와 의견을 같이 하는 사람. 손들. 같아? 같아요? 두 사람. 나머지는? 영서는?
제가 본 마르코브 이퀄리티랑 조금 노테이션이 달라서.
아, 노테이션이 달랐는데 이해를 해야 된다니까? 노테이션을.
이해를 못한 걸로.
근데 이거 most fundamental한 거잖아. 그지? 셋에서 어사인먼트 이게 우리가 배웠던 거. 그지? 샘플 스페이스에서 매핑한 게 랜덤 베리어블이라고 했으니까. 그리고 거기에 디스트리뷰션이 붙어 있는 거고. 저걸로 이해를 해야 돼요. most fundamental이라고. 승민.
네.
1 or 2?
2번 하겠습니다.
2번. 야, 이쪽에 많이 붙네. 자, 그러면 우리 한번 성규가 한번 설명을 해줘. 왜 2지?
아 이게 근데 사실 x가 0보다 크거나 같다는 조건이 있어야 되겠고
뭐라고?
x가 0보다 크거나 같다.
이 그림. 이
맞습니다.
그림. 요게 이게 우리가 사실 이게 렛이지. 렛. 이렇다고 한 가정하에서 물어보는 거지.
그러면 오메가가 AT에 안 들어가면 왼쪽 거는 0이 되고 뭐 x
그러면 그 우리가 여기다가 그림을 한번 그려봅시다. 아, 빨간색 없나? 파란색은 안 보일 것 같고 하얀색으로 그려봅시다. 얘를 첫 번째 거에 대해서 그려봅시다. 얘는 뭡니까? 여기다가 그리면 뭐예요? 그대로?
아니 t까지 줄여가지고
그렇지. 얘는 오메가 1일 때 오메가 1이래. 근데 오메가 1이면은 뭐죠? 1이죠. 얘는 왜? 오메가 1은 x 오메가가 t보다 큰 셋에 속하잖아. 그러니까 얘는 1이야. 그죠? 그런데 t가 앞에 붙어 있잖아. 곱하기로. 그러면 얘는 어디까지예요? 크기가 여기까지지. 여기까지. 그죠? 그 다음에 또 오메가 2는 이때는 0이라고 그랬잖아. 왜? t보다 작은 x 오메가가 t보다 작아. 그 셋에 속해. 그러니까 요 케이스지. 그럼 0하고 곱한 t는 0이고. 그러니까 얘는 0이죠. 그죠? 그 다음에 오메가 3일 때는 same song and dance죠. 한번 했으니까. 이거지 뭐. 그죠? 그럼 for each 오메가, x 오메가가 항상 같거나 크지. 그래서 아하, 얘는 날려버리고 이렇게 되는 거죠. 됐죠? 이게 말코브 이니퀄리티. 여기에다가 expectation을 양변에다가 취해. 그게 텍스트북에서 말하는 말코브 이니퀄리티. 그러면 이쪽이 뭐가 되죠? t는 상수니까 밖으로 뺄 수 있고 expectation of 요거는 뭐죠? expectation of 요거는 expectation of 이 셋이지. 그 셋은 요거니까 expectation of 이 셋은 요거니까 probability로 바뀝니다. 그래서 x 오메가 그래도 된 t로 바뀌고 t 곱하고 이게 나옵니다. 이렇게도 한번 생각해 보세요. 뭐 다른 방법도 많지만 그 원론적인 방법에서 한번 즉 우리가 처음에 시작한 거 있잖아. 그 primers of probability 내가 만들어준 노트 그거 가지고 다 드라이브가 가능하다. 그러면 오늘은 거기까지 하고 마치겠습니다. 네. 네.